Hello everyone, I am Upala Mukhopadhyay from Shah Institute of Nuclear Physics, India. At the very outset, my sincere thanks to the organizers for giving me this opportunity to present my work in this conference. The title of my work is Probing Interacting Dark Energy and Scattering of Baryons with Dark Matter in Light of Ages 21 cm Signal. My collaborators are Devashish Majumdar from Shah Institute of Nuclear Physics and Kanan Kumar Dotto from Presidency University. And this is the reference of this work. First, I will discuss the main objective or motivation of this work, and then I will discuss very briefly the formalism we have considered, and then I will show the results we have obtained, and in the end, I will discuss the conclusions, and you may have few take-home messages. Okay, so what is 21 centimeter line and why is it very important? The 21 centimeter line arises due to the hyperfine splitting of the ground state level of neutral hydrogen atom. This hyperfine splitting arises due to the interaction between the magnetic moment of electron and proton. And why this 21 centimeter line of hydrogen atom is very important? Because it is a very useful tracer to understand the properties of galaxies and intergalactic medium, because we know that almost 75% of the known mass content of the universe is hydrogen. Moreover, it is also a very important probe to understand the physics of universe in the ages of cosmic dawn or cosmic dark ages. Cosmic dawn is the time when the first stars have started to form, and cosmic dark age is the time between the CMB decoupling and the cosmic dawn. In fact, the ages observational results show an anomaly between the theoretical prediction and the observational results corresponding to the 21 centimeter line of cosmic dawn. And this probably indicating some new interesting physical phenomena. I will come to this point later. Okay, so in cosmology, 21 centimeter line is used as a probe along the line of sight of a radio object. So here we consider it as the CMB radiation. And when the CMB photon passes through this hydrogen gas, it interacts with it. And in the detector, one may have this TCMB plus an additional delta TB. This delta TB, which is attributed as T21 or T21 signal, is defined as the difference between the spin temperature and the CMB temperature. And also it depends upon the optical depth of the gas, this tau. And we can see that if the spin temperature is greater than the TCMB temperature, then we will have an emission spectrum. And if TS is less than TCMB, then we will have an absorption spectrum of 21 centimeter line. So what is the spin temperature? This is nothing but the excitation temperature of 21 centimeter line, and it is defined by the ratio of the number density of hydrogen atoms in the hyperfine energy levels. Okay, so this is a schematic diagram of the dependency of the spin temperature Ts on different quantities. It depends on the TCMB, it depends on the kinetic temperature or the gas temperature, it depends upon the Lyman alpha temperature. Okay, so this is the ages observational result, which shows a large absorption feature at the cosmic dawn centered around this Z equal to 17. And they reported that the values of T21 lie between minus 0.3 Kelvin to minus 1 Kelvin in this region. But according to the standard cosmological model, the value of T21 should not be less than minus 0.2 Kelvin for this region. So here comes the anomaly between the theoretical prediction and the observational result. So to explain such excess absorption trap, one may invoke a few new physical phenomena which can explain either a smaller spin temperature or a larger background temperature or a larger optical depth. So in our work, we have tried to explain this excess absorption feature by considering two interacting scenarios: interacting dark energy scenario where the dark energy interacts with dark matter, and dark matter baryon interaction. Actually, due to the interaction between dark matter and dark energy, the evolution of the universe would be modified, and that would modify the evolution of Hubble parameter, the densities of dark matter and dark energy, and that would eventually modify the T21 signal. And due to the interaction between dark matter and baryon, heat will flow from baryonic fluid to the colder dark matter fluid, and thus the T21 would be affected. So therefore, we have considered these two interacting scenarios and try to investigate that whether this can explain or not the larger unexpected absorption feature reported by the edges observational result. Okay, in this context, we have also tried to give constraints on the model parameters of interacting dark energy and dark matter. Okay, so now I have come to the formalism part. The interaction between dark matter and baryon fluid would affect the heating rate of baryon or heating rate of dark matter. So here the heating rate of baryon, dQB dt, can be written as the sum of these two terms, where this first term comes due to the temperature difference between dark matter and baryon. And this sigma naught is the interaction cross-section of the dark matter and baryon fluid. And the second term comes due to the velocity difference between these two fluids. This dV chi b is the dragging term. This dragging term arises to damp the relative velocity, and that will have an heating effect on both of the fluids. Okay, again, the interaction between dark matter and dark energy will also have an impact on the brightness temperature of 21 centimeter line. If we consider the interaction between dark matter and dark energy, then the continuity equations are given as this, where this Q is the energy transfer between dark matter and dark energy, and rho chi and rho d are the energy densities of dark matter and energy densities of dark energy. But due to this interaction between dark matter and dark energy, rho chi and rho d do not evolve in their usual form, that is proportional to 1 plus z cube or 1 plus z to the power 3 into 1 plus omega, where omega is the equation of state for dark energy. And therefore, the evolution of the Hubble parameter would be modified, and it will no longer have this usual form. And as the effect of this, the optical depth, which is inversely proportional to the Hubble parameter, would be modified. Not only the optical depth, actually all the quantities which involve the Hubble parameter or the energy densities of dark matter or dark energy would be modified. So therefore, this heating rate of baryon or heating rate of dark matter, optical depth, and all the other quantities would be modified, and these all will have an effect on the brightness temperature of 21 centimeter line. Okay, so in our calculation, we have considered these three well-studied phenomenological model of interacting dark energy. These three models are already there in the literature. We have taken these into account for our calculation. This lambda is the DMD interaction parameter. And this table shows the constraints on the model parameter of these three models. And these constraints come from the other experimental results like Planck data or supernova type 1A data, BAO data, and etc. So we will try to investigate that whether an interacting dark energy model, which is well in agreement with the other experimental constraints, could also be consistent or not with the AJ's observational results. So our approach is to solve these four coupled equations to obtain the temperature evolution of baryon or the temperature evolution of the spin temperature. So the first equation is for the temperature evolution of dark matter. This first term comes due to the expansion of the universe. This second term is for the dark matter and baryon interaction, and the third term is for the dark matter and dark energy interaction. Similarly, for this equation, the first term is for expansion of the universe, the third term is for the dark matter and baryon interaction, and the second term is for other heating and cooling effect. And as these two equations depend on the free electron fraction, we should also consider the evolution of the free electron fraction. And this is this third equation. And these two terms correspond to the recombination effect and photoionization effect. And we should also take into account the variation of relative velocity. So we have solved these four equations, not only these four equations, along with these two equations, that is, we have solved these six coupled equations to obtain the evolution of the baryon temperature. And in cosmic dawn, actually, TB is identical to the spin temperature due to the Wuthering field effect induced by the Lyman alpha photons. So therefore, by solving these six coupled equations, we have obtained the spin temperature of the hydrogen gas, and thus the brightness temperature of 21 centimeter line. Okay, so now I have come to the result part. Here I am showing the evolutions of Hubble parameter for three interacting dark energy models we have considered. And okay, from here we can see that for positive values of DMD interaction parameter lambda, the value of Hz is smaller than the standard value of the Hubble parameter. Okay, so from here we can predict that for larger values of lambda, we can have a larger optical depth. Okay, here I'm showing the variation of the delta T21 with the DMD interaction parameter. Delta T21 is defined as the T21 minus T21 0, where T21 0 is the 21 centimeter brightness temperature at Z is equal to 17.2 for the standard lambda CDM model, and this T21 is the same for the our model, that is when all the interactions are taken into account. Okay, so and this the region between these two black lines or the region below these black lines are indicating the value of delta T21 for which the edges limit will be satisfied. So from these plots, we can see that when the values of lambda are larger, then we can have a larger absorption signal of T21, and which can reduce the discrepancy between the theoretical prediction and the experimental observational data. Similarly, if we consider sigma 41 is equal to 0, okay, and here sigma 41 is the interaction cross section between dark matter and baryon in 10 to the power minus 41 centimeter square unit. So when it is 0, that is when there is no interaction between dark matter and baryon, then the edges limits are merely satisfied. But if we consider sigma 41 is not is equal to 0, that is an interaction between dark matter and baryon is present, then delta T21 can satisfy the edges limit for different values of lambda. So these three plots are for the model 1 of interacting dark energy models. Okay, this is the same plot for the model 3 of interacting dark energy models. And we can see that the edges result can be satisfied when the strength of lambda is greater or equal to minus 0.04. But it is shown from other experimental result that the upper bound of lambda is 0.00989. So the values we need to, the values of lambda we need to satisfy the edges experimental result do not corroborate with the values of lambda obtained from the other experimental constraints. And this is the same case for model 2 of interacting dark energy. And therefore, these two models are in a big tension. Okay, so this is the allowed parameter space of dark matter mass and DMD interaction parameter for model 1 of interacting dark energy model, where this color coding is showing the temperature of brightness temperature of 21 centimeter line. And from here we can see that for larger values of lambda and for smaller values of m chi, the edges results can be satisfied in a more favorable way. Okay, and this is the allowed parameter space for sigma 41 and m chi, and here we have taken two cases, lambda is equal to 0.08 and lambda equal to 0. Lambda is equal to 0 means there is no interaction between dark matter and dark energy. And from here we can observe a interesting fact that when there is no interaction between dark matter and dark energy, then m chi can probe up to around 3 GeV. But when we consider an interaction between dark matter and dark energy, then m chi can probe up to around 8 GeV. So when the interaction between dark matter and dark energy is present, a larger mass range of dark matter can be probed to satisfy the edges observational result. Okay, so here is the summary of this talk. We have tried to explain the unexpected absorption trough of edges experimental result of 21 centimeter brightness temperature by considering two interacting scenarios, dark matter dark energy interaction and dark matter and baryon interaction. And we have found these three major points. First is larger dark matter baryon interaction cross section, larger dark matter dark energy interaction parameter, and smaller dark matter mass are more favorable to achieve the edges observational result. The second point is model 1 of interacting dark energy can satisfy the edges result and the other experimental result together, but it is not the case for the other two models, and therefore the other two models are in a bit tension. And the third point is DMD interaction raises the possibility of probing larger mass range of dark matter to achieve the edges observational data. And that's all. Thank you for your patience and interest.